Hello, this is Stat134, Lecture 6. So last time, section 2.2, we talked about the normal approximation of the binomial. And remember that for binomial, the mean is NP, and the standard deviation sigma is square root of NPQ, where Q is 1 minus P. And because most of a normal distribution has its data between mu plus or minus 3 sigma, we require, if we're going to approximate the binomial by the normal, that n and p be such that mu plus 3 sigma is between 0 and n. Because remember that for binomial, the outcomes of the binomial, of a binomial distribution, are between 0 and n. So otherwise, your distribution, your normal distribution, will be cut off at one tail or the other. So, and also we require that n be large. So those two things. Now today, we're going to finish section 2.2, covering the law of large numbers, and then we're going to cover section 2.4, skipping 2.3, which is going to be about the Poisson approximation. So the law of large numbers is captured by one of these two pictures, and it's captured by the bottom picture. So in the bottom picture, it's about the proportion of successes. So let's say that you are flipping a die, or you're rolling a die a certain number of times. The chance of getting a 6 is truly 1/6. Now the proportion of successes that you get when n is 60 will be a broader distribution than when n is 600. That's the law of large numbers, and that's the opposite effect of when you're just looking at the number of successes. So we saw a concept test last time that showed that the chance of getting exactly 10 sixes out of 60 is greater than the chance of getting exactly 100 sixes out of 600. That in that case, we're not applying the law of large numbers. We're applying the top picture here, where we see that the spreads become greater as n increases. So the law of large numbers says that the proportion of successes goes to p as n goes to infinity, where p is the probability of success. So why is that the case? Well, let's call the proportion of successes our estimate. So you may not know what p is, then you would estimate that by the proportion of successes. So the average of that estimate is just p, whereas the standard deviation of the estimate is the square root of pq over the square root of n. So we see that the standard deviation of the estimate is going to have a n in the denominator. And so as n gets larger, the standard deviation or spread is going to become smaller. Great. So now we're going to go on to section 2.4, which is about the Poisson approximation. So just in a word from this picture here, remember these are binomial for different p and n. And when is it that we apply the normal approximation? It's when sort of p is between 0 and 1 towards the middle. We require n be large, so that's the highlighted in the middle case. Now, when you're on the ends here, we're going to apply the Poisson approximation. So the Poisson approximation is about having n be large and p be very small, close to 0, or p being close to 1, but we'll talk about that situation in a moment. So for the cases when p is smaller, p is close to 1, and n is large, we approximate binomial np by Poisson mu equals np. So Poisson is going to have one parameter called mu. Now the definition of Poisson mu is we're going to have infinitely many outcomes between 0 and infinity, but they have to be integers. And the probability for a fixed parameter mu that I have k is e to the minus mu times mu to the k over k factorial. So here's an example. So say you bet 500 times independently on a bet with 1 over 1,000 chance of winning. So n is large, 500. I should even underline independently here because that's important because we need binomial to apply. And p is 1 over 1,000, which is small. So what's the probability that you win greater or equal to 1 bet? So the probability that you win greater or equal to 1 bet is 1 minus the probability that you win nothing. And we can do this two ways. We can do it exactly using the binomial. So the binomial is 1 minus p of 0, where p of 0, apply the binomial formula, and we get 0.3936. Or we can apply the Poisson here with mu is np. So mu is 1/2, and we get 0.3943, so quite close. Now what about those binomials with p close to 1? Well, if p is the chance of success, q is the chance of failure. If p is close to 1, then q, which is 1 minus p, is close to 0. So binomial nq can be approximated by Poisson mu equals nq for large N, small q. So here's an example. So 97.8% of approximately 3 million families in the U.S. have a fridge. If you randomly sample 100 of those families, roughly what's the chance that 98 or more have a fridge? So P is a probability that you have a fridge, 0.978, N equals 100, that's large. Now, P is close to 1, so what we're going to do instead is look at the number of failures. So the probability, we're asked to find the probability that 98 or more have a fridge, but that's equal to the probability that 2 or less don't have a fridge. So don't have a fridge is a failure. So Q is 0.022, and we can then approximate our answer. I should write here approximate, right? So I can approximate my answer using the, actually it's not here, it's here that I want to approximate, using Poisson to get 0.6227. So here's a helpful picture to see how, for example, Poisson 1 is a limit of binomials as binomials where p goes to 0 and n goes to infinity and np goes to 1. So these are the requirements that we have here. So take a look at binomial 10, 1 over 10. So this says mu is 1. Binomial 100, 1 over 100. This also says mu is 1. Binomial 1,000, 1 over 1,000. This also says mu is 1. But n is getting larger, p is getting smaller, and you can see that these binomials are kind of converging towards what is actually going to be the Poisson 1. So fantastic. So then, why is it that the binomial converges to Poisson? Actually, you can see it mathematically. So it follows from two key facts. One is that one is that the binomial, so I'm fixing n here, so binomial k is 0 is approximately e to the minus mu. And secondly, we have a recursive relationship between pnk and pnk minus 1 given here. So using these two facts, pn of 1, we can find from pn 0, it's pn of 0 times mu over 1. And then similarly, pn2 is pn1 times mu over 2, which is e to the minus mu times mu squared over 2 factorial. So in this way, you can see how you're getting the Poisson distribution. So the proof of fact 1 and fact 2, I've written out in great detail here, and I'd like you to read this. It should be completely clear to you. Then we did a concept test, and I asked you, recall that NP plus P is used to test for the mode of a binomial. The mode of Poisson 5 is A, 5, B, 4, and 5, C, 0, 1, D, none of the above. So most of you said it's 5, which would be incorrect. It's actually 4 and 5. So the correct thinking about this is that for binomial, see, one of the nice things about Poisson is that it borrows, because it's a limit of binomials, is that then things that you know about binomials transfer to what you know about Poisson. So for example, binomial, if n is the floor of np plus p, then the mode we know about binomials is either m or m minus 1 m, depending on whether np plus p is an integer or not. Now, for Poisson, p goes to 0 and np goes to 5. So only mu equals 5 is necessary to find the mode for Poisson. So for Poisson mu, if m is the floor of mu, the mode is either m or m minus 1 m, depending on whether k is not equal to mu or k is equal to mu. Now we have the